Okay, Assalamualaikum warahmatullahi wabarakatuh. Right, and good day everyone. Okay, so we are going to proceed with conjugate direction method, where we are going to discuss specifically on Fletcher Reeves method. Okay, so before this, in SD, which is steepest descent, we have discussed about the zigzag phenomenon. Okay, where the moving process from the initial point to the solution point is about zigzag phenomenon. So let's say this is the curve, this is the solution point. So towards the solution point, it moves almost every step in terms of right angle. So by using the derivative, so this one use derivative. Okay, and then in terms of hook and jive, the movement process is through right, left, up and down, in front and back. Okay, so now in terms of conjugate direction method, it moves again, still it moves toward from the initial point to the solution point by conjugate direction. Okay, so how will the conjugate direction move? Okay, so we are going to discuss about this method. Okay, so now conjugate direction is used as a direction search, where we consider this problem. We want to minimize the problem. Let's say this is for quadratic function. So this is a general form of quadratic function where A is a symmetric positive definite matrix. Okay, so in 2 dimension, the contours of fx equals to k for any value of k is an ellipse with the same center. So let's say we have the contour, okay, of ellipse here. This is C, this is B, okay, so this BC is conjugate to AD. So this is what we call a conjugate angle. Okay, so now this is to simplify the figure here. So assume that we want to find a minimum point from A to D. Okay, from point A in the direction D, we want to find the minimum point. And the minimum occur at the point B. So let's say this is minimum point. Okay, it occurred here at B. So C is an optimum point. We say that the direction BC is a conjugate to direction AD because for any ellipse, here is any ellipse for fx equals to k, the diameter passes through B is conjugate to the line parallel to D. So instead of zigzag movement in SD, by using the right angle, we are now moved in terms of conjugate direction. So as you can see, the angle is getting bigger. So it is believed that the process to move to the solution point is getting faster. Okay, so this is the surface idea about how the conjugate direction move. Okay, okay, now let's see about the method. Okay, so for Fletcher Reeves, right, this method use mutually conjugate direction. Okay, we want to find the minimum point, the solution point. So this method overcome the disadvantages of DFT, which generates mutually conjugate direction by using H. So we want to avoid of calculating H matrix, Alright, so we use this conjugate. So it overcomes the disadvantages of finding the matrix one by one for each iteration. Okay, then it generates mutually conjugate direction by using vector formula that can be used for a general function. Okay, now let's discuss this. Consider the quadratic function. Okay, so this is a quadratic function, the general form of quadratic function. Alright, so we see our search along direction which are mutually conjugate with respect to A, which are P1 and P2. So this is the conjugate direction, okay, which mutually conjugate with respect to A. Okay, so the first point, x1, so we start with our initial point, is met in the direction of steepest descent. So usually x1 is given, but this is met in the direction of steepest descent. Okay, where P1, we start with P1 equals to negative G1, where G1 here is the derivative, okay, which is equal to negative AX1 plus B. Right, then once you got your P1, you can have your X2, which is given by X2 equals to X1 plus lambda 1 P1. So how can we obtain lambda? Just like the previous method, where we need to find the value of lambda that minimize the function. So lambda I is obtained from the steepest descent orthogonal direction search property. Okay, so where G1, G2 equals to 0, P1 transpose times G2 equals to 0, where P1 transpose times with AX2 plus B, where this G2 is AX2 plus B, just like this one. If G1 is AX1 plus B, so G2 here is AX2 plus B. Okay, where AX2 plus B here is given by AX1 plus lambda 1 P1. So this is your X2, this one. Okay, this is equivalent to minimize the function at X2 with respect to lambda 1, which must be used if the function is non-quadratic. So instead of minimize the function by using this to find lambda, now we can find the value of the function here by minimize the function at x2 with respect to lambda 1. This one. Okay, so this is applicable for the function which is non-quadratic. Then once you obtain the value, then we can generate the direction of P2. So this direction is accelerate by using this gamma, where the P2 here now equals to minus G2, the derivative, plus with lambda 2 times P1. So this is how it accelerates the movement process. Now we have another coefficient instead of lambda only. Now we have the gamma 2. Okay, where that gamma is a scalar. We must choose gamma 2 such that P1 and P2 are mutually conjugate with respect to A. Okay, so we want it to be conjugate. P1, P2, and then again it moves. So this must be influenced by the value of gamma here. Okay, that is P1 transpose times A P2 equals to 0, which equivalent to minus P1 transpose A G2 minus gamma 2 P1. So this is actually P2, right? This one is the conjugate characteristic, where just like above, we have G1, G2 equals to 0. So when it is mutually conjugate, all right, then the dot product equals to 0 here. So just like this, we have P1 transpose AP2 equals to 0, where this P2 is given by G2 minus gamma 2 P1. And the P1 here is obtained by negative x2 minus x1 transpose lambda 1, where we obtain this from above here, this one. Okay, so substitute, this is just a derivation process. So we simplify and then we get this or this. Okay, but G2 transpose P1 equals to 0. G1 transpose G2 equals to 0. This is because P1 equals to negative G1 and G2 and G1 and G2 are orthogonal to each other. So simplifying this, by using this information, we will get this. Okay, so observe that gamma 2 here is independent of A and hence can be evaluated as a general function. So to generate the direction search, all right, so let P3, now we want to generate the direction search. Let P3 equals to negative G3 plus gamma 3 P2 plus mu 3 P1. All right, so this, why gamma 2 here is independent of A, hence we can evaluate as a general function. So to generate that, we equal to this P3 minus G3 plus gamma 3 P2 plus mu 3 P1. Okay, well, now P1, P2 and P3 are conjugate of A. So this is just the vector. So this is just the scalar where all of these three, P1 and P2 and P3 are conjugate of A. So we have another P there. That's why we have another P there in order to get P3. Okay, so therefore, the value of these two, okay, which are conjugate equals to 0. So substituting what is P3, which this one, okay, and then substitute and then we simplify to get the value of mu 3. Okay, so this is just a simplification process where mu 3 is G3. This one, just substitute what is your, this is G3, this is A, so this is your P1, P1 transpose. Okay, and then this one is your P1, right? So substitute here and then simplify what is this. So substitute by G2 minus G1 transpose. Then we know that P1 equals to negative G1. So substitute again and we will obtain this. So P1 minus P2 equals to negative G1 plus G2 minus gamma 2 P1. So we obtain G2 from here. We simplify G2 minus G1 equals to negative P2 plus 1 plus gamma 2 P1. That is orthogonal to G3. Okay, so because this is the product of this P and G here equals to 0. Hence, it is orthogonal. Okay, where I and S equals to the value there. Okay, therefore, mu 3 equals to 0. And we have P3 equals to this. So this propose the formula. Okay, by looking at this one by one, generally, it can be simplified to this function where Pi is actually minus Gi plus gamma I, Pi minus 1 and gamma I is given by Gi transpose Gi divided by Gi minus 1 transpose Gi minus 1. So this gamma is used to calculate the conjugate direction. Okay, so the value of mu here is just another scalar for the next iteration. So as you can see, at each iteration, where is the mu there? At each iteration, it moves conjugately with a scalar. Okay, so start with lambda, and then we have gamma, and then we have mu. So to simplify all of those things, then we use this formula of conjugate direction. Okay, now let's try to take a look at the example by looking at this algorithm. All right, so we want to minimize this function of fxy. We have two variables here, 1 minus 2x minus 2y minus 4xy plus 10x squared plus 2y squared, with the starting point given 0, 0 and epsilon equals to 0. So the stopping criteria is epsilon equals to 0. Okay, let's try by looking at the algorithm here. Okay, step 1, right? We decide our x1. Okay, let xi be initial point. So x1 is given by 0, 0. Okay, then find g1. So g1 is given by derivative of fx1. So we need to have the derivative of f here, where derivative of f here is given by del fxy here. So just differentiate this with respect to x and with respect to y partially one by one. So we have minus 2 minus 4y plus 20x. Okay, and then another one, minus 2 minus 4x plus 4y. So for g1, just substitute x1 here. Then we will have 2, 2. All right. So set P1 equals to negative G1. Set Pi equals to negative Gi. So now when I equals to 1, so P1 equals to negative G1, which equals to 2, 2. Sorry, this is negative 2, negative. Okay. So now this is your G1, negative 2, negative 2, and P1 is negative G1. So we have 2, 2. All right. Then we want to calculate x2. Okay. So before we find this, we have to have x2. So x2 is given by x1 plus lambda 1 P1, where x2 equals to 0, 0 plus lambda 1, 2 and 2. Okay, so this is your x2, where it equals to 2 lambda 1, 2 lambda 1. So substitute this x2 to f. All right, so just substitute the point here to function f here. Then we are going to have fx2, which is equals to 1 minus 8 lambda 1 plus 32 lambda 1 squared. Okay, I just omit the writing style here so that you can differentiate one there with the power. So this is fx2. Okay. So if you want to find the value of lambda, find the value of lambda that minimize the function. So you have to have del f del lambda 1 equals to 0. So solving this just like our previous example in steepest descent in Newton so on. This is the process of finding lambda value. So solving this will give you minus 8 plus 64 lambda 1 equals to 0. So lambda 1 equals to 1 over 8. So substitute this value to here to get your x2. Hence, your x2 equals to 1 over 4, 1 over 4. Okay, and find your G2 just substitute the point of x2 in G here. Okay, then G2 is given by 2, -2, right? So calculate epsilon by 2 squared plus -2 squared, which is not equals to 0 yet because our stopping criteria here is 0. Then proceed again with finding P2. Okay, next step is what? We find G2, we find gamma, and we find P2. So we need to find gamma 2 here, gamma 2, and then we have to find P2. So gamma 2, okay, proceed here, I proceed here. So gamma 2 is equals to G2 transpose times G2, G1 transpose times G1. Okay, so G2 transpose times G2, 2 minus 2, 2 minus 2, G1 is what? Minus 2 minus 2 will give you 1. Okay, you check after this. So once you've got the value of gamma, then find P2, where P2 equals to negative G2 plus gamma 2 P1. Substitute. Substitute the function here. So just substitute here. We have negative G2, G2, negative G2. So minus 2 minus 2 plus 1. And P1 is 2, 2, which give you 0, 4. So why we have to find P2 here? Because our G2 is not fulfill the stopping criteria. So we need to proceed with the next iteration point. So in order to proceed with the next iteration point, we have to have P2. And this P2 need to have gamma 2. So that's why we have to calculate gamma 2 first and then P2. So from here, you can find again your x3 goes to x2 plus lambda 2 P2. Again, same process. So you have to find your x3 here, where x2 is 1 over 4, 1 over 4. Lambda 2 still is unknown, and P2 is 0, 4, which give you 1 over 4 plus 0 and 1 over 4 plus 4 lambda 2. So this is your x3, and then you just substitute to your function of f and minimize the function, where fx3 here is 3 over 8 minus 12 lambda 2 plus 2, 1 over 4 plus 4 lambda 2 squared. Okay, so from here again, minimize the function. So we need to differentiate this f with respect to lambda 2, equal it to 0, and find the value of lambda 2, which is equals to 1 over 8. So from here, once you get your lambda 2, you can have your x3 because you already have your x2 and p2. So x3 equals to 1 over 4, 1 over 4 plus 4 times 1 over 8, 3 over 4. Okay, once you got your x3, just substitute to your g to get g3. So g3 equals to now 0, 0. Once you substitute x3, substitute to g3, where g is the derivative function of f, and you can have epsilon equals to 0 from this. So the minimum point is obtained at x3, where x3 is 1/4n, 3/4, and fx is given by 0. Okay, so this is the process of finding the solution point by using Fletcher Reeves. So the idea here is to use the accelerate value of gamma, okay, in order to move conjugately so that the angle will be widened. Okay. All right. So this is two variables in your notes. Right. So I hope you can understand this. This is quite identical with the previous method, but with some little bit different approach. Okay, so in the notes, I have shared to you the process use up to 3 variables, but still same process. Okay, you can try the example here. Okay, let's go one by one through this example. So this one, we have a function of 3 variables, x1, x2, and x3. Okay, so the starting point is given. All right. And the epsilon here is given approaching to 0. Okay, usually the epsilon value is given in the question, so don't worry. Okay, now let's understand this. Same process with the previous one, but in the previous one we have 2 variables, so now it is up to 3 variables. So first, of course, you start with your x1, okay, and then calculate your g1 by differentiate your f. Okay, then differentiate your f. So this is the general form of derivative function of f here. Then just you substitute the point of x1. So you got your x1, you got your g1. Okay, x1, g1, and p1 is negative g1. So we always start p1 with negative g1 by this algorithm. All right, now you can have your x2. So x2 is given by x1 plus lambda 1 p1. Again, substitute what is given. So you have to find lambda 1 by substituting this x2 to your f, so that you will have fx2. And then that lambda should minimize the function, so you need to differentiate f with respect to lambda equals to 0 and find the value of lambda. Once you got the value of lambda, you can have your x2. So when you have your x2, then you can have your g2. So in this g2, you can check the magnitude of g2 in order, is it reaching the stopping criteria yet or not? Okay, then not reach the stopping criteria, then we continue to the second iteration. So in the second iteration, there is the calculation of gamma, okay, where we need to have gamma because we want to have P2. So we have to calculate gamma first, where the gamma is given by G2 transpose G2, G1 transpose G1. So calculate this, then you get gamma 2, and then you can have your P2. So this is your P2. Why you want to have your P2? Because we want to calculate our x3. Again, same process. Calculate x3, substitute, find lambda 2, substitute to fx3, simplify, differentiate equals to 0, and find the value of lambda. And you can have your x3, and then you can have your g3. So once you substitute to g3, always check the magnitude of g and then compare with the epsilon. Once it reach the value of epsilon, so this is approaching to 0, then we stop the iteration. Okay, then the minimum point is obtained, where the minimum value is obtained from the minimum point. So this is how we calculate the Fletcher-Reeves method. All right, so thank you. Assalamualaikum.